Thank you very much. So I'm very honored to give this talk. I would have loved to be with you, of course, but okay, so I'm not able to do it. So so my talk is about a joint work with Patrick Graf and Henri Guenancia, and it concerns essentially ball quotient, as you will see in a second. So here is a short plan of the talk. So I will begin with a gentle introduction with the recalling the smooth case, and then I will move to the singularity we will need to face in some sense, so the KLT pairs and the orbifold Chern classes of this pairs, and I will end with a sketch of proof of the uniformization result we got. Okay, so so let me recall the smooth case. So here I will look at the unit ball, and also I pick a lattice, a co-compact lattice in PU11. This is the automorphism group of the ball, and I assume first that the action is free. So it means that this guy is a smooth, sorry, up. And so this is a smooth projective manifold. And actually, so Kx is ample. So for instance, it comes from the fact that the Bergman metric is invariant under gamma, and so it gives a metric with positive curvature on this line bundle. And we have the Hirzebruch proportionality principle that says that essentially the Chern classes of X are the same as the up to a constant that does not depend on I. So these are the same as this, the compact dual of the ball, that is the projective space. And for Pn, we know very well the Chern classes, and it's very easy to check that this relation holds. And okay, so the magic of the Keller geometry is that we can go the other way around, and so this is the numerical characterization given by essentially Aubin and Yao. So according to this people, we know that if Kx is ample, then we can find a unique, actually, but we don't need the uniqueness here. So we can find a Keller metric with negative Ricci curvature, and exactly the Ricci of omega is minus omega. And now we can use this Keller-Einstein condition for omega, and we compute the Chern classes of X with respect to omega, so the C1 and the C2, and we compute this whole expression. And actually, so I should have written like that. So actually, so this is a punctual. So sorry, my pen is not very good. So this is a punctual identity. When I say that, I mean at the level of Chern forms. So so this quantity 2n plus 1 C2 minus n C1 square wedge omega to the n minus 2. So this is essentially, so here it just means that there is a constant. So I hope this constant is something like that. Maybe there is a square on the pi, but and so up to this constant, so this quantity is nothing but the square norm of the traceless curvature tensor. So theta 0 is the traceless curvature tensor of the metric omega. And so, of course, this quantity is non-negative. And what you get is, sorry, if the equality holds So this is just a cohomological constant, but so it can be computed using this integral. If this quantity is 0, then so we deduce that, of course, the corresponding L2 norm is 0. And so it implies that the traceless part of the curvature traceless part, sorry, of the curvature tensor is identically 0. And so the curvature tensor is reduced to this its trace, and this is exactly this is the Ricci curvature of omega. And so we get at the end that the curvature is constant, and once we know that, it's easy to conclude that X is a Ball quotient. Okay, so I just want to give a second proof of this characterization of the equality case in the Miyaoka-Yau inequality. So it appears in the works of Carlos Simpson. So it's needed to, so we consider this bundle, so omega 1 plus O, and so it can be ended up with this map, and this theta is so this is a map from E to E tensor omega 1. And so this has the property that theta H theta is 0, so it's very easy to check it with this formula. And so this E theta is the so-called X bundle. And so it was observed that if Kx is ample, then this X bundles is X tables. And so we have this Bogomolov-Giesecker inequality for E theta, and this is exactly our preferred quantity that is non-negative. And in the equality case, so this X bundles actually underlies a principal variation of our structure, and the corresponding projective period maps gives an isomorphism between X tilde and the ball. So I just wanted to present this proof because, in a sense, this is the one that we can use in the singular setting. Oops.
Can I ask you a question? The second part, that's
sorry, the sound is really bad.
Sorry. The second part, your second statement on the previous slide.
Yes, on the previous slide. So this one.
It's stable. I was only able to do that for a surface. So that must be due to somebody else. Is that you or?
So this one?
Yeah, yes.
So, okay, so you say that I should attribute it to someone else?
I think so.
Okay. I will think about it. Okay, so I'm a bit lost here in my slide. Okay, so now I come to the singular case. So here, when I say singular, I mean what happens if we drop the free assumption? Okay, the freeness assumption. So in that case, of course, our X Bn mod gamma is singular. Of course, it has very mild singularities since it's only quotient singularities, but we would like to work in a more general setting, and of course, so this is the first point. So we would like to identify a natural class of singularities to work with, and okay, so now this is more or less clear that we should work with KLT singularity. Sorry. So here it stands for Karamata log terminal. And so I will explain in a second. So what does it mean? So the other point is that we have to work with pairs. So here we have to encode something in a Q divisor. So here delta is an effective Q divisor. And so this delta, it encodes so the ramification in codimension 1. Of the natural projection Bn to X. And so, of course, in order to get an exact analog, so we have to define Chern classes, or at least Chern numbers, in this singular situation. Okay, let's do this way. Okay, so now I move to to the singular setting, and first I just want to discuss very briefly the orbifold things. So if U is smooth and G is a finite group acting on U, then we can form the quotient, so X to be defined as a U mod G, and so this is normal, of course. And so there is a natural Q divisor defined on X, and so it has the so-called standard. So these are called standard coefficient. So of this shape, 1 minus 1 over an integer. And so what are the MI? So the MI are exactly, so it's the ramification order of the projection, so identified by F, so from U to X, along any component of the pullback. So since the morphism is a Galois cover, then if you pick any component, then you will get the same result for the ramification order. And so we have this. So we can think of it as the Hurwitz. So this is just Hurwitz formula, but this is very important for what follows. And so from now on, I will say that a pair X delta is an orbifold if X is a complex normal space, delta an effective Q divisor, so with standard coefficient, meaning that exactly 1 minus 1 over m, and such that locally X delta is built as above as a quotient by a finite group, and of course we have to add a compatibility condition. Okay. And now I move to KLT pair. So so this is a definition that comes from the MMP, of course. And so a pair is called Karamatalogue terminal. So if X is normal, delta is an effective, sorry, I forget. So this is an effective veil Q divisor. And we assume that this a priori only Q veil divisor is actually a Q Cartier. So meaning that a multiple of M kx plus delta is Cartier, is the line bundle. And we also assume that, so this is the general definition. So the round down of delta is 0, so the coefficients are less than 1. But for us, so this is this will be automatic if delta has standard coefficient. Okay, so this is the first point, and the second one. So we have to compute this kx plus delta on a resolution. So since kx plus delta is Q Cartier, so it makes sense to put it back, and we compare this line bundle to the line bundle kx hat plus. So this is a strict transform of delta. So we compare these two guys. Of course, the difference is supported on the exceptional divisor, and we ask that the coefficient appearing here, so these are called discrepancies, are strictly greater than -1. And so there is, so it can be translated into a purely local analytic, let's say, definition. So it's the same as the existence of, okay, let me write it like that. So we have existence of section of this line bundle, of course. So this is the existence is just local, such that this quantity so it converges. So when you integrate these things on the regular part of X minus delta. Of course, so here X is not the whole of X. So it's the small open set on which sigma is defined, if you prefer. So you can write it like U. So it amounts to saying that we have some kind of integrable volume forms. Okay, so let me give some examples of KLT pair. So of course, an orbifold is a KLT pair. So if U is Bn, then we can look at tau to be so Ng, sorry, Ng a subgroup of GLN C. So active, or maybe it's better to have a subgroup of UNC, so it acts on the ball, and so we can look at so this form. So you take the tensor product of the translate of the usual form, and so it leaves. So it's a G invariant M section of M K U, where M is the order of G, and so it defines something on X, and sorry, and of course it's easy to verify this integral converges. Okay, so it gives you the fact that these quotient singularities are KLT singularities. And in fact, it's so in the case if delta has a standard coefficient, okay, if not the whole sentence does not make sense, so standard coefficient. So in that case, so if you start with the KLT pair with standard coefficient, then in codimension 2, so if you remove something of codimension 3, then the complement is an orbifold. And so it has the following consequence. If X is a surface, then KLT exactly corresponds to orbifold, to quotient singularities. And so this is the first point, and the second point in general. So if the dimension is greater than 3, if you pick a surface S defined as the intersection of n-2 hyperplanes, so if HI are ample hypersurface in X. So here I assume that X is projective. Then this surface is you have to assume also that HI is general, of course. Then S will be contained in this X naught, and the restriction of the orbifold structure of the KLT structure is an orbifold. Oops. Okay, so you see that KLT, in some sense, KLT are not so far from being quotients, and this is this not so far that we want to quantify in the rest of the talk. So I just add this other example. So this is really something. It's a kind of slogan. So if you look at a cone or something, so in general, so this is KLT, if and only if the base is fine also. So it say that KLT singularities has to do with they have to do with Fano, or at least with singular Fano sets. Okay, so for us, so I have to explain so what this why this kind of singularities are interesting, and so maybe a good explanation is, at least, so if you are concerned with with topological questions, you have this this very let's say interesting result of Brown that say that if you look at the germ of projective KLT singularities, then the pi1 of the regular part of a neighborhood, of a sufficiently small neighborhood, is finite. So this is the reminiscent from quotient singularities. So of course, so it was so there were this result as an history, and the previous result by Shen and Shu. So it was in 2014. where he proved that, okay, so Xu wasn't able to prove that the finiteness of this group, but at least the finiteness of the profinite completion of something a bit smaller. So the pi1 of the link. So Xu was able to prove that the pi1 of the link has only a finitely many finite quotients. So I explained that. So because else you could wonder why this Greb-Québécois-Péternel sync in 2016 is a consequence of a result in 2021. This is because Greb-Québécois and Péternel used Xu's result to prove that. But once you have Brown results, it's very easy to get this these things. So this is a very useful tool that we will use in the rest of the talk. So once you have a projective variety with only KLT singularities, then you can find a quasi-étal cover. So it means that there is no ramification in codimension 1. And this Y has this wonderful property that you can compare the pi1 of the regular part of Y and the pi1 of Y itself. But of course, this is not a complete statement. You have to put at everywhere. So the profinite completion of the pi1 of Y is the same as the profinite completion of the pi1 of the whole space. And okay, so it essentially says that so they have both groups, they have the same finite quotient. But it says a bit more. We will see in a second. So in the remaining, the remaining of the part of the talk, so such a Y will be called maximally quasi-étal. Okay. So let me just explain an example. So if you look at the Kummer surface, so this is just you mod that here A. So this is an abelian surface, and you mod that by a plus or minus 1. So you have this projection. So it's 2 to 1, and so this X is singular, and it's not hard to compute the pi1, and this group is trivial. But if you look at the pi1 of X, X reg, and the regular part of X, then you see that it gives you an étal cover between the restriction of pi gives you an étal cover when you restrict it to the complement of the two torsion points of A. And so it exactly of course the pi1 of A minus A2, this is the same as the pi1 of A. So this is this Z4. So the pi1 of X reg is very, very big. So it's virtually abelian of rank 4. But hopefully this map is quasi-étal, and so it gives you the maximally quasi-étal cover. Okay, just a point in general. So there is no quasi-étal cover with this property, with the pi1 of y array. Okay, so essentially it comes from the fact that we can find examples where this group is not profinite. So starting with this observation, we can build examples where it never happens. Okay, I just want to reformulate the existence of this quasi-étal, this maximally étal cover, sorry. And for us, the interesting reformulation is the following. So if you replace x with y, then for this y, you have the property that any linear representation defined on the regular part of y factor through the pi1 of the whole space y. So given rho, there exists a rho y defined on the pi1 of y. And the reason is nothing but Malchev result that says that finitely generated subgroup of G and C are residually finite. So once you know that, it's easy to show that you have this property of factorization. Okay, now it's time to define the orbifold C2. And there is at least two different ways to define the orbifold C2. The first I want to present is the Mumford construction. And so here I wrote it for the C2 of a pair. So here, of course, since I consider a very ample line bundle on X, so from now on, I assume that X is projective. And then we can look at a complete intersection surface, S, so where HI are in the linear system defined by A. And as we said, this surface, it sits in this orbifold locus. And so it's tempting to define, you see that it's hard to define this as a cohomology class. But we can define a number. So this is, it's better to say that it's a linear functional, a linear form on, let's say, H2. A multilinear form. Okay, so this construction can be also applied for an orbisheaf. So if F naught is let's say an orbisheaf or an orbi thing, so defined on the orbifold locus, then so what Mumford did is that we can find S hat to S, so a finite Galois morphism such that the pullback of this guy restricted to S. So you take the reflexive pullback. So this guy is locally free. And then we can define the C2 orbifold, the Mumford C2 of this F as you have to divide, of course, by the degree of the cover. And here you take the C2 of the pullback. So you just have to be aware that this S hat is in general singular and very singular. So because this Galois cover is obtained as as a normalization in some function field. So it's very unexplicit, and but at least it exists and it gives a number. And so it has also the advantage to stay in the algebraic setting. Okay, so because here when I write this C2 orb, so I think of these things as an orbifold, and so I compute this C2 orb using the Chern theory. Okay, so speaking of this Chern thing, so let me add this. So this second construction, so that was explained by Graf and Kirchner. So I still look at the orbifold locus of the pair, and so they remark that since the codimension of the Z, so that is the complement of X naught, is at least 3, then we have this abstract isomorphism. And so we can use it to compute again not a Chern class, but at least the Chern number. So we want to compute this C2 at X delta against alpha to the n minus 2, and so I consider this this alpha to the n minus 2 as an element of this. So this is, so I use the cup product. So this is an element in the H2 n minus 4. And so using this abstract isomorphism, so I can see it as a 2 n minus 4 forms. Now it's a since we are on an orbifold, we can use orbifold forms. And so this is really a form with compact support. So I can represent it by a form with compact support. And if H is any orbifold metric on the orbifold part of X, again, I can compute a Chern representative of the C2 orb. And so it gives you, so the wedge product gives you a class that has compact support in X naught. So I can compute the integral. And it gives you a number. And the point is that, so as was observed by Graf and Kirchner, so both definition coincides. So if you prefer to stay in, or if it's more useful to stay in the algebraic setting, then you can use Mumford trick. And in the analytic setting, it's certainly easier to compute it like that. Okay, so let's come to the to the generalized Miyaoka-Yao inequality. So it was proven that by Henri Guenancia and Verustagi, that if you start with a KLT pair, so as always with standard coefficient, and we assume that the canonical bundle of the pair, so Kx plus delta, is big enough, then we have formally, so we have the same inequality. So 2n plus 1 C2 C2 hat minus N C1 hat, oh, sorry, square X delta. And when you pair this quantity with Kx plus delta to the N minus 2, then you get a non-negative number. But there is this, so it could seem as a strange assumption. So the fact that the fact that any component of delta is assumed to be Q Cartier. So I will explain in a moment why this is necessary. But of course, if you don't want to put that assumption, you can always assume that X is Q factorial also. It's another way to phrase this assumption. Okay, now so since we have the inequality, it's rather natural to look at the equality case. And so what we prove with Patrick and Henri is that the same happens as in smooth case. So if Kx plus delta is now supposed to be ample, and again, so each component of delta is Q Cartier, then once we have the equality in the inequality, then the pair is a Ball quotient. And so of course, if X delta is a Ball quotient, so when I write it like that, so I mean that delta is the ramification locus of the projection. Of course, it satisfies the equality.
Does it satisfy that each component?
Does it satisfy that each component of delta is Q Cartier?
Yeah, in that case, X is Q factorial. Since when X is an orbifold, this is the space X is Q factorial. Am I right?
Yes.
Okay, so just a few words about the history, and also it's in some sense it's a motivation for this work. So in a quite old paper now, so Cheng and Yao proved the orbifold version. So and so a few years later, so it was proven by Kobayashi, Nakamura, and Sakai that this inequality for the using the KLT setting in the surface case. So of course, if you remember, I said that in the surface case, sorry, let me use the right color. So surface case, so we said that KLT is nothing but orbifold singularities. So this result by Kobayashi, Nakamura, and Sakai is in some sense contained in Cheng and Yao, but here in that work, so delta is allowed to have purely logarithmic, so to have essentially so coefficient equal to 1 on some component. So it corresponds to, geometrically, it corresponds to the case where when the surface is an open surface, it's a quasi-projective surface. And so later on, so quite recently, so Greb, Québecus, Peternel, and Tadji proved the previous result, but when delta equals 0, and so actually, so there were 2 papers, So I hope something like 2018. So when X is KLT, but also smooth in codimension 2. So the singular locus has codimension 3. And then they drop this assumption on the codimension of the singular locus. But in that case, so you see that the conclusion can be written like that. So there exists gamma lattice in P, U, and 1, such that X, of course, is Bn with respect, modded by gamma, and so gamma acts freely in codimension. So 2 in case 1. So you don't want singularities in codimension 2. So you have to assume that gamma acts free in codimension 2, or 1 in case 2. And so, so you see that even in this general KLT case, if delta is non-zero, then you come out with a with a restriction on the action. And so at least as far as I'm concerned, I really wanted to drop this freeness assumption, and that's why we have to work with the in the pair setting. Okay. And so maybe I forgot to mention here. So the open case. So I mean, in the quasi-projective case, it was also recently studied by Yadeng. Okay, so let me give some hints on the proof, and so here is the main ingredient of the proof. So first, so this is the solution of the Zariski-Lippmann conjecture. Let's say that if you have a KLT variety, and if its tangent sheaf is assumed to be locally free, then X is smooth. So this is really important. So it has been proven by Jeb, Québécois, Kovacs, and Peternel, and later on also by Druel in some more general situation, and then Graf and Kovacs, and so on. Okay, so we already saw this guy. So the maximally quasi-étal covers. So in that case, we have this isomorphism, and for us, in terms of flatness, it says that. So it exactly says that a flatness on X only need to be checked on the regular part of X. And that's, okay, it sounds really, really useful, this kind of thing. So this sentence exactly means that if you have a sheaf on X, a reflexive sheaf on X, and such that its restriction to the regular part is flat, then your sheaf is actually flat on the whole of X. Okay, and so we will also need the singular version of Simpson correspondence, so explained in the next slide. And in our case, so when delta is non-zero, we will need to use the so-called adapted cover. So let me say a word on this singular Simpson correspondence. So it was proven by Reb, Québécois, Peternel, and Tadji in the last paper on on the topic. So if X is as always a KLT projective variety, A an ample divisor, and on this X, so we consider a reflexive X sheaves, but only defined on X reg. But we also consider its reflexive extension to X. So we didn't. So here it's important to note that we suppose that everything is algebraic, so that the extension is coherent and so on. And with this data at end, so we have the equivalence between these two propositions. So this X sheaves is polystable, X polystable with respect to A. So only defined on the regular part of X, but we can compute the slope and so the slope of this guy and of the sub X sheaf, since everything is defined on the regular locus. So it has a meaning. So this polystability has a meaning on the regular part of X, and so we ask this guy to be polystable, and this vanishing of the Chern, let's say Chern classes, SH1 and SH2. So these are the orbifold analog, and this is equivalent to E-reg being locally free, and this X bundles being induced by the so-called purely imaginary harmonic bundle structure, whose monodromy is semi-simple. So essentially, so it relies on works of by Mochizuki. And so I just want to explain the upshot that we will use. So you see, if 2 happens, so if this guy is locally free, and since it's induced by something, essentially by a representation, so it says that this guy is flat. And now if X is maximally quasi-étal, we have just said that this is equivalent to saying that E itself is flat on X. But the flat thing is so the interesting point is the flat thing is locally free. In particular, so it implies that E is locally free also. So this is what we are going to use in the for the proof. So here is the sketch of the proof. So you will see this is quite easy with all the stuff at end. So we start with this cover. So this is a so-called delta adapted cover. So it has the property that the branching loci of F is supported on delta, and you also have to add some extra branch. And so you can assume that this extra branching is supported on an ample divisor. Okay, and so it has the property that it ramifies at order mi over delta I. So in some sense, it's an unfolding of the orbifold structure. And so these things always exist and always exist. And it can be constructed using a cyclic cover. And this is exactly where use the fact that delta I is Q-Cartian. So this is exactly, this is the only point where we use this assumption to construct this, this delta adapted curve. Once we have that, we can forget about this Q-Cartier assumption, but it's needed from the very beginning of the proof. Okay, and so I will denote by n the ramification order of f along H. And so what is important is that since H is ample, so it moves in a base point free system. So we can use that to check that this new pair delta plus this 1 minus 1 over H is still KLT. And this is very important because, for instance, using the Hurwitz formula for F, we see that the canonical bundle of Y is the pullback of the orbifold downstairs, but this modified orbifold. But since F is finite, so Y is KLT as well. And so we stay in the realm of KLT singularities, and so we will be able to apply this Simpson correspondence, singular Simpson correspondence on Y. And so how does it work? So as in the smooth case, so we consider the usual Orbi-X bundles. So this is the cotangent of the orbifold. So maybe it would have better to put here x0. So it's the orbifold cotangent bundle, and I had a copy of the trivial one. So really this is the same as in the smooth case, and so it was proven by Guenancia and Tadji that this Orbi-X bundle is still polystable with respect to this. So let me remind that now the Kx plus delta is assumed to be ample. And we look at this complete intersection surface in X, and so I pick my hyperplane in this in the linear system associated with a multiple of my ample canonical bundle, and since S is chosen in this linear system, we obviously get that the Chern of the second Chern character of F naught restricted to S is 0, and here F naught is the endomorphism of this X bundle. And now it's time to get rid of the boundary. And so to do that, we go to the cover Y. So since F is finite, this divisor is still ample. And so this F, since F is an unfolding of delta, this pullback, this reflexive pullback, this is now a Jenin sheaf on Y. On Y not. And so here Y, okay. And this Y not, this is the big open set of Y. And of course the stability, so it can be checked that the stability is preserved. So with respect to this new polarization. And the point, okay, it's not very deep, but it took us a long time to be sure that it's true. So we still have this identity. So the second Chern character in the orbifold sense of F naught with respect to this polarization is 0. And so the whole point is that, sorry, I'm lost in my notes. So the whole point is that so we can consider T the pullback of our surface S. And now we have the map between S from T to S. So this is a finite cover. But this is not an orbifold cover for delta, but for this modified pair. But the point is that these Chern classes can be computed using forms, and these genuine forms are these orbifold forms are genuine forms on the regular part of S minus the support of delta. Okay, so orbifold forms are a genuine form on S reg minus delta restricted to S, and the same for this modified delta. And so when we compute the pullback, when we integrate the pullback of this form, we obviously have this the multiplicativity by the degree, and so the fact that this equality holds downstairs, then it has to hold upstairs also. And so we see that we are in good shape. So f naught y, so defined on a big open set of y, and so it's stable, polystable, and it satisfies the Chern classes equality. And so it says that these things, it extends as a locally free sheaf on the whole of y. And now it's easy to conclude, because what is this fy? So if you stay away from this additional ramification, so this fy, I said this is an unfolding of the orbifold structure. So this is nothing but this quantity. Okay, so we get rid of the delta, and so this is the usual endomorphism of the X sheaf. And now it's if you look at this guy, so this endomorphism thing, so you see that Ty is a direct summand of this endomorphism sheaf, and so it's also locally free away from this pullback of H. And by Zariski-Lippmann, it exactly says that this open set is smooth, and so since the Galois, since the cover y to x is Galois, it says that the pair x delta has quotient singularity away from H. But now H is an ample line bundle, and it can be chosen freely at the very beginning of the argument. So we can move it as we want on X. And so finally, we get that X delta has quotient singularities everywhere, and we are done. And thank you for your attention, and sorry for being late.